Yeah, so let me repeat that again. So like I was saying, once Linda is a friend of Benjamin, Benjamin is a friend of Caleb, then the result of the relation will be you're going to have a suggested relation from to Linda that Caleb might also be what? A friend, okay? Yeah. Yeah, so let me just take the diagram here. So what we are saying here is if one moves to two by the relation R1, you see this is 1, 2, okay? And by the relation R2, we have 2 to U. Then it means that one maps to what? To U, or one is related with U, okay? Good. The same way, if one moves to or is related with 6, and 6 is also related to T, then it means that one is related to what? To T. Okay, so this is it. Now, if 2 is related to 4, and 4 is related to 6, to S, sorry, then it means that 2 is related to what? To S. Then 2 is related to 4, 4 is related to T. So it means we have 2 related to what? To T. The same way 3 is related to 4, 4 is related to S, so we have 3S. 3 related to 4, 4 related to T, so we can have 3T. 3 related to 8, 8 related to U, so we can have 3U. Okay, so that gives us the set of the composition of the two relations R1 and R2. I hope explanation is clear now, Jacob.
Yes, sir. Thank you so much.
Okay. I think some of your friends are off. Let me just assure them we are still in class. Okay, let's continue. So we have basically 4 types of relations. Okay, technically we have 3 because one is the opposite of the other. But as you see here, we've expressed 4 types of relation based on the subsequent analysis we're going to do. Okay, so we have reflexive relation, we have the symmetric relation. Okay, when a relation is not symmetric, we say it is anti-symmetric or asymmetric. Then we have the transitive relation. Okay, what do we mean by these forms of relation? Okay, good. Now, when we talk about, let me move to the next page. Okay. So when we say a reflexive relation, reflection is just looking into the mirror, okay? So you look into the mirror, you see yourself, yeah. So what we are saying is if a relation is like this, we move from 1, and then 1 maps back to a relation 1 in Y. X is 1, and then it maps to 1. Then such a relation is a reflexive relation. And we write it as what? We write it as what? X belonging to what? The set R. Okay? So that is what we mean by reflexive relation. Good. Then the next one is symmetry. Okay, symmetric means you divide the 2 and you get 2 equal halves. So for example, you have, no, let me use a very basic example. Okay, I have this line. I have X here. I have Y here. Okay. I even want to use numbers 1 and I have 2 here. Now, if I divide this line, okay, I'm going to have 2 equal distances. Okay. I'm going to have 2 equal distances here. Okay. Good. So let's say I have A in here. Good. Then it means that we should be able to have 1. Okay. So symmetry just means you partition and then you get 2 equal what? 2 equal halves. Okay. And in the context of our study, what we are saying is if you have X to Y in what? In R, belonging is a member of R, then you should also have Y to X in R for the set to be what? For the set to be symmetric. Okay. So if you have X in Y belonging to R, then Y and X should also what? Belong to R. However, if there is a situation where X, Y belongs to R, but Y and X does not belong to R, then we say that the relation is what? Anti-symmetric, okay? We say that a relation is anti-symmetric. Okay, then finally, for the last condition, we have transition. Transition simply means, let me clear this first. Okay, so when we talk about transition, it's like we are moving from, let's say, point A to point C. Okay, the focus is to move from A to C. This is the intention. But some way, somehow, we had to go through point B first, maybe because of traffic or something, okay? So we move to point B and then we move to point C. Yes, we still end at point C. So we've achieved our motion, okay? But what we are saying is all these 3 relations should exist to have what we call as transition, okay? So there should be A to C. We should also have A to B. We should have AB. And then we should also have what? B and C. Okay, all in R. They should all be in R to have what? A transitive relation. If one of them is not in R, the relation is not transitive. Okay, so you take note of that. All these 3 should be in R at the same time. Okay, if even one is missing, then the relation fails to satisfy the condition for transitiveness. Okay, let's proceed. So I want to look at some few examples. It says determine if the following relations are 1, symmetric, reflexive, symmetric, anti-symmetric, or transitive. Okay, so we're going to take, I'm going to take question 1. You try the rest as an assignment for me. Okay, so for question 1, the set first, you need to get your set of the relation R. So R is, the rule says what? X squared should be greater than or equal to Y. Okay, good. But now you should have mastered X is what? 1, 2, 3, and what, 4. Okay. And then you can see we have been told that R is on 1, 2, 3, 4. Okay. So if you told R is 1, 2, 3, 4, then it means that both the domain, which is X, and then the range, okay, or the codomain is all on what? 1, 2, 3, 4. So we have 1, 2, 3, and what? 4. Okay, that is what we have been told. Good. So here we have the rule says that x squared should be greater than or equal to y. So when you square x, it should be greater than or equal to y. Okay, so let's start the analysis. 1 square is equal to 1. Okay, is equal to 1. So we can have that relation existing 1, 1. But 1 square is not greater than 2, okay? Neither is it greater than 3 and 4. Okay, the rule says x squared should be greater than or equal to y. So let's go to the next one. 2 squared is what? 4. Okay, now 4 is greater than 1, right? 4 is greater than 2. 4 is greater than 3. And 4 is also equal to 4. Okay, so we can have those relations existing. We have 2, sorry, let me clean that. So we have 2, 1, 2, 2, 2, 3, and then we have 4, 2, 4. Okay, good. Now take note, it is not a 4 you are pairing. 4 is the square of the x. Yes, in the pairing, you only indicate x and y, not x square. The rule says x square, okay? But in the set, you pair the x and y. Good. Then what about 3? 3 square is 9. Yes, indeed, 9 is greater than all these values here. So we can have more pairings. That is what? 3, 1, 3, 2, 3, 3, 3, 4. Good. The same way 4 square is 16, which is greater than all the numbers there. So we can have 4, 1, 4, 2, 4, 3, 4, 3. Okay. And then we have what? 4, 4, 4. Okay. So these are the pairings in what? In R. Very well. So you've been asked to determine if the relation is reflexive, symmetric, anti-symmetry, or transitive. Okay. Good. So let's check for reflection. Reflection means we should have X pairing back to itself. Okay, belonging to the set R. Okay, good. Yeah, and then clearly when we check, we have 1, 1 here. We got 2, 2 here. We have 3, 3 here. We have 4, 4 here. Okay, good. So let me skip to the next slide. Yeah. So we're saying that since the elements 1, 1, 2, 2, 3, 3, 4, 4 are members of R, then R is what? Reflexive. Good. Now, what about symmetry? Symmetry says that for symmetry, we said if X and Y, the parent X, Y belongs to R, then R both must exist. Then Y, X should also what? Be in R. Both must be in R. It's a must. Okay. So let's go check. We have 2, 1 here. Okay. If X is 2 and Y is 1, this is X, this is Y. X is 2, Y is 1. Do we have Y to be 1 and 2? Okay, there is no 1 and 2, okay? So we cannot have 1 and 2 in what? In R. Okay, hence we say that R is what? Is not symmetric. Not symmetric means anti-symmetric or asymmetric. Good. Now let's come to the very final condition. Final condition is transition. Transition, we said we should have 3 points. 3, so if you're moving from X to Z and you pass through Y, then you should have 3 parents, all in R. You should have X, Y. You should have Y, Z. And then you should also have what? X, Z in R. Okay, they should all belong to what? They should all belong to what? To R. Okay, good. So let's go and check. So when we come here, let's pick probably 2, 2 and 3. So X is 2, Y is 3. Then let's take YZ. Y is 3, so Z should be another number. So we have Y, which is 3, and then Z is 4. So X is 2, Y is 3, and then Z is 4, right? So we have XY here. We have YZ. Do we also have XZ? SZ should be 2, 2, 4. Okay, because Z is 4 and X is 2. So do we have 2, 4? Let's check. Yes, we have 2, 4 here. Okay, so we got 2, 4 here. It means that we have a transition. Okay, a transition between 2 to 1. Sorry, 2 to what? 3. This is X. This is Y. And then Z is what? Z is 4. Okay, so there's a transition from 2 to 3, 3 to 4, and then we also have 2 to 4. Okay, so the transition word exists. Very good. So then we know that this relation is reflexive, it's anti-symmetric, and then it's what? Transitive. Any question? Any question? Okay. Okay, very well. I guess that is clear enough with the absence of any questions. Okay, good. And once again, we can also do this analysis, okay, using what we refer to as digraphs, directional graphs. Okay, so if you're given the sets and you have reflection like we just solved here, let's go and plot the digraph for the previous example. So for this example, you had 1, 2, 3, 1, 2, okay, let me put 3, 4 here. Then I can put 5. Let me put 5 in the middle. No, it's only 1 to 4. So no 5. So we have the relation 1 to 1. 1 to 1 is going to be a loop back to itself like this. Okay. We also have 2 to 2. That will also be a loop. So anytime you have a loop, we are referring to what? Reflection. So this is also a loop. Then we have 2 to 1. So there is a relation 2 to 1. There is, we've already indicated 2, 2, 2, 3, 2, 4. We have 3, 1. We have 3, 2. We have 3, 3. We indicated that. Then we have 3, 4. We have 4, 1. We have 4, 2. We got 4, 4, 3. 4, 3, and then 4, 4 finally. Okay. Now in digraphs, loops represent reflexiveness. Okay. Then when we talk about symmetry, symmetry is where you have this double arrow. So like 2 to 4, 4 to 2. Okay. 3 to 2, 2 to 3, 3 to 4, 4 to 3. But you see, we have 1, 2 violating symmetry. We don't have an arrow back from 1 to 2. Okay, good. In graph theory, we'll say a path from 1 to 2. Okay, good. And similarly to 1, 3 also violates symmetry. That is why we call the whole graph what? An anti-symmetric what? Relation. Okay, good. On the other hand, when it comes to transitive, I mean, there is a satisfaction from all angles. So 1 to 2, okay, 2 to 4, 4 to 3. We have 1 to 2 to 1, 2 to 4, 4 to 1. Okay, so transitive is what? Transition is established, okay, or achieved in this set. Okay, so that is it for the concept of relations. We're left with the very final aspect of relation. Now, any relation that is a partial, that is reflexive, antisymmetric, and transitive at the same time is called a partial order, meaning there is partial ordering. Okay, good. So if the relation is reflexive, antisymmetric, and transitive, we call it partial order. Okay, and to identify that is simple. You just have to check if R is 1 reflexive, 2 antisymmetric, and 3 transitive, like we've just done in the previous example. Okay. On the other hand, if the relation is reflexive, symmetric, and transitive, then we call such a relation an equivalence relation. Okay, good. So if the relation is reflexive, symmetric, and transitive, then we call the relation what? An equivalence relation. And it's also simple. All you need to do is to check if the relation is reflexive, whether it's symmetric, and whether it's transitive, like we did in the previous example. Good. Now, let me take one or two questions before I move on to the next topic. That is, if there are any. If there are any questions, you can raise your hand before I move on to the next topic. Okay. It appears everything is clear. Okay. Yeah, so we want to move on to the concept of functions. Which is topic 3. Okay, so that is the OUR notes lecture 3. Good. And like we said, the focus here is we want to look at what a function is, how it is written, the notation, visualization, okay, or what you refer to as graph of functions. We'll look at a type of functions, or what you refer to as mappings, and which mapping is indeed a function. Then we also look at inverse functions, and finally composition of functions. Good. Now, a function is a type of relation, okay, but there are two unique things about a function, okay. The first thing is there should be a domain clearly defined, okay, for the function. And then secondly, the image of a function should be unique, okay. The images generated from the function should be unique, okay. So those are the two characteristics of a function. A function is indeed a function if a domain is clearly defined and there is a unique image, okay, to the function. Good. So we are saying that if there are two elements, y and x, y and y bar as images, then y will have to be equal to what? Y bar, if f has to be a function, okay? That's the uniqueness of the image. Now, the functional notation, sometimes written as f maps, the function maps an element in the domain to elements, okay, y, which is your range, okay? Or we write it computationally like that. F of x is equal to what? Is equals to y, okay? Good. Very well. So in other words, if it's written like this, then if you define a function f of x is equals to let's say 3x, okay, then what we're saying is then essentially y is also equal to what? Is equals to 3x, because f of x is equals to what? Is equals to 3x, okay? Very well. Let's move on. Okay. So we have, like we said, this can also be represented using arrow diagrams, okay? We can also represent our functions using arrow diagrams. Very well. Now, we want to go on to graphs of functions. A number of you have logged off. We're looking at the graph of functions. Okay, how to plot a graph of a function. We have an example, f of x is equals to x squared plus 1. And the domain has been stated as what? X should be greater than or equal to what? To 0. Okay, good. Now, like we are aware, there are, let me say, two main techniques of plotting functions. Okay, we can plot it using the numerical approach or using iterative points. Okay, and then we can also plot this function using a differential word approach. Okay, good. But we're going to demonstrate it using numerical approach. Okay, numerical approach, what I mean is you select few points within the domain. The domain has been clearly stated as x greater than or equal to 0. Okay, so it means our domain starts from what? 0. So we got 0 inclusive. So we got 0 to what? To infinity. Okay, good. So it means that if we're to select points on this graph, it's going to be x, and then f of x here, or what we refer to as y. Okay, we have 0. Let's just select arbitrary point, 1, 2. Let's select 3, and probably 4. Okay, using a numerical approach. Then you do the evaluation, okay, of f of x. So f at 0 will give us what? 0 squared plus 1. Okay, 0 squared plus 1 should give us 1. Good. Same if we do f at 1. F at 1, we're going to get 1 squared plus 1, which is going to be equal to what? 2. Okay, good. Then similarly, we have f at 2. F at 2 will give us 2 squared plus 1, which is equals to what? Which is equals to 5. That's 4 plus 1 equals to 5. Okay. Then we have f at 3. F at 3 will be 3 squared plus 1, which is equals to what? 9 plus 1, 10. And then 4 squared plus 1 will be 16 plus 1, which is 17. Okay, good. So then we can plot this graph. Okay, let me pick an eraser. So we find an eraser, we clean this portion, and then try to graph this. Okay. So we choose, you can choose a suitable scale. In exams, I'm going to give you graphs and ask you to identify the graph of the function. Okay, good. So I'm going to take you a little step further. Okay, since it's most likely we may be having an open book exam, I have to take you a bit deeper. Okay, good. So you have 0, you have 1, you have 2, you're going to have 3, and then you have what? 4, and so on and so forth. It goes to, S goes to infinity. Okay, good. And when you come here, you have 1 to 17. So possibly we can choose 0.5, we have 0.10, we have 0.15, we have 0.20. Okay, for your y. Very good. So this is x, this is y. Okay. Now when we check we plot the points. We have 0, 1. Okay, so we have 0 and we have 1 here for the first point. We should have started 0 from here, right? So let me change that. So I have 0. Let me change that quickly. So let's have 0. Okay, at the intersection, whilst we have 1. This should be 2. This should be 3. This 4. Okay, and 5. Okay, yeah, that is better. Then we have 0, 1. We have 1, 2. We'll have 2, 5. 2, 5 going this way. We have 3, 10 going that way. And then we have 4, 17. So 4, 17 will go that way. Okay, so clearly when we look at, we visualize this graph, we can see that this graph is what is, it's a parabola. Okay, so this graph is a parabola. Okay, very good. Now, like I said, there are many types of different ways of doing this. We could have also used the graphical, the differential approach, okay, where you differentiate the function, check for the minimum and the maximum point or the turning point, okay, and determine whether it's concave up or concave down. That will also help you to plot a graph of a quadratic function. Good. Then again, I'm going to introduce you to other forms of function, which we call as a piecewise function. Okay, so we can also have a function denoted piecewisely over certain domains. So I have a function, let me say x squared, or let me even put it as 2x, okay, given that x is between 1 and 3, okay, and then the function is x squared plus 2, or yeah, just make it simple. So x squared, okay, where we'll have x is from, yeah, x is greater than 3. Let's put it that way. Okay, very well. So we refer to this as piecewise function, meaning it is defined piecewisely. Okay, so on this domain, we have a different value of the function. So on this piece of the domain, the function is 2x. But on this other piece of the domain, the function is what? X squared. Those are the type of functions when you're writing a program, you are programming, you use the while loop, or you use the if x is between 1 to 3, okay, then the function y is equals to this, else that, or if x is between 1 to 3, the function is 2x, else if x is what? Less than, is greater than 3, the function to be x squared, okay? Then you end, and then end the function again to give you the graphical demonstration, okay, of what you have, or the computation of the value of the function. So in this case, this function is going to look like this. On this piece, we are going to have x